Beneath the tallest building on Earth, engineers faced the one thing no skyscraper should ever meet: 50 meters of shifting desert sand, eager to swallow concrete whole. The Burj Khalifa wasn't just risky, it defied geological logic. If even one pile or pour failed, the entire tower could have slipped beneath Dubai. Why take this gamble? And how close did they come to disaster? In 2004, engineers faced a nightmare beneath the Dubai desert. The ground was nothing but layers of loose sand and soft rock, stretching down more than 100 meters, with no solid bedrock in sight. Every expert knew what that meant. Any weight above would press down, and the earth below would simply give way. The world's tallest building needed legs that could grip shifting sand, legs that would not slip, tilt, or sink under 500,000 tons. The answer was friction piles. Teams drilled 50 meters down, deeper than a 15-story building, using massive rigs that churned up the desert. But every borehole threatened to collapse the moment it opened. To fight back, crews filled each shaft with a thick, muddy slurry denser than water, which pressed against the walls and stopped the sand from pouring in. Into that unstable darkness, they lowered steel cages and poured in high-strength concrete, creating 194 giant piles. Each one depended not on hitting rock, but on the rough grip of sand clinging to its sides. But piles alone could not spread the tower's weight. Above them, engineers built a raft, a slab of reinforced concrete 3.7 meters thick, wider than an Olympic swimming pool. Pouring it was a race against time. Each of the 4 stages lasted more than 24 hours without a single break. If the concrete cooled unevenly or work stopped, cracks would form, and the entire foundation could be lost. Hundreds of workers labored day and night, mixing ice into the concrete to keep temperatures down in the desert heat. When the final pour set, the Burj Khalifa finally had a stable platform, legs sunk deep into sand, and a foot broad enough to hold up the impossible. Wind at 800 meters isn't just strong, it's unpredictable, swirling with enough force to twist steel and shatter glass. For a structure this tall, the danger isn't just from gusts, but from something more insidious: vortex shedding. When wind hits a smooth vertical surface, it peels off in swirling eddies, creating powerful pulses that can set a building swaying back and forth. Over time, these invisible whirlwinds can shake a skyscraper to the point of structural failure. The standard solution, making the building thicker or stiffer, would have turned the Burj Khalifa into a squat, inelegant block. Instead, the structural designer at Skidmore, Owings, and Merrill studied the desert itself. The answer came from the hymenocallis, a native flower with 3 radiating petals. The Burj's Y-shaped plan, with 3 buttressed wings, mimics this form. Each wing steps back at different heights, breaking up the wind's path as it rises. No 2 sides are the same for long. As the wind climbs, it can't find a rhythm. The swirling vortices that would batter a normal tower are scattered, their energy lost before it can build up. Wind tunnel tests confirmed the effect. Compared to a plain cylinder, the Burj Khalifa's setbacks and irregular geometry cut peak wind accelerations by nearly half. Computational fluid dynamics models showed the building would stand nearly motionless, even as desert gusts hammered its flanks. With the shape set, the next challenge was making sure the core could resist these forces, a problem that would demand new materials and construction methods as the climb continued. Construction hit its stride in 2005. With the foundation locked in place and the wind problem solved, crews launched the vertical sprint. The heart of the Burj Khalifa, the central concrete core, rose faster than any skyscraper before it because of a breakthrough in building technology, self-climbing jump forms. These bright yellow platforms acted like moving factories, pouring, shaping, and curing concrete as they inched themselves up the structure. Once a floor was finished, the forms would grip the edges, hoist themselves up, and start again. The result? A new floor every 3 days, week after week, as if the building itself was learning to grow. Working at this pace demanded absolute discipline. The core foreman, leading a team of hundreds, kept the rhythm unbroken. Day and night, workers poured high-strength concrete into the ever-rising molds. Every batch had to reach a precise strength before the next lift could begin. The process was relentless, but the momentum was undeniable. By 2007, the rising tower passed 452 meters, overtaking the Petronas Towers to become the tallest building in the world. Yet the climb was far from over. As the structure soared higher, each new floor added weight and complexity. Materials had to travel farther, and the challenge of delivering concrete to such heights grew more intense with every meter. But the jump form system held the pace, driving the project forward. The Burj Khalifa was no longer just a vision. It was a living, growing reality, racing skyward on the back of a construction rhythm the world had never seen. Concrete wants to flow downhill. Gravity, friction, and heat all work against you when you try to send it straight up. On the Burj Khalifa, the challenge was to push wet concrete higher than anyone had ever dared. 601 meters, nearly 3/4 of a kilometer, into the sky. The answer was a Putzmeister BSA 14,000 SHPD super pump, a machine built to handle pressures up to 200 bars, forcing concrete through steel pipes bolted to the building's side. The pipeline twisted upward, floor after floor, as the tower grew. But the higher it went, the more friction built up inside the pipe, heating the concrete dangerously. Too much heat, and the mix would crack as it set. The solution was almost surgical. Blocks of ice were dumped into every batch, keeping the temperature low enough to survive the climb. Even then, the mix had to be just right. Polycarboxylate superplasticizers made the concrete flow like liquid without extra water, so it stayed strong. Every pump cycle was a gamble. If a pipe burst at that pressure, it could slice through steel. But the team kept the flow steady, breaking the world record for vertical pumping and delivering concrete to heights no one had reached before. The concrete skeleton needed a shield, one that could survive the desert's glare and the wind's fury. Crews began the painstaking process of cladding the Burj Khalifa with 24,348 glass panels, each engineered with a silver coating to bounce back the sun's relentless heat. Every piece had to fit perfectly, not just for looks, but to keep the interior cool and safe. At the peak of installation, teams managed to set 175 panels a day, working floor by floor as the tower swayed beneath their feet. Out on the swing stages, workers dangled hundreds of meters above the ground, tethered by harnesses and nerves. The wind could gust without warning, turning a routine lift into a fight for balance. Dust storms swept in, coating everything in grit. Gloves slipped on hot metal. Each panel weighed more than a person, and a single mistake could send glass crashing down the side of the building. Yet, day after day, the crews pressed on, transforming bare concrete into a shimmering icon, one dangerous step at a time. Concrete could only take the Burj so high. At 586 meters, the switch to steel began. Above that, the final climb belonged to the world's tallest cranes. Machines so high that operators slept in their cabs because climbing down each day would take too long. The steel spire, nearly 140 meters tall, was too heavy and too unwieldy for any crane to lift in one piece. So engineers built it inside the tower, stacking the sections like a collapsing telescope. Hydraulic jacks hidden within the core pushed the spire upward in careful stages. Each lift was a gamble against wind and gravity, but section by section, the spire emerged until the building reached its full height, 828 meters. Now a new problem loomed: how to get the cranes down. No machine on Earth could reach them. The solution was as precise as it was strange. The cranes took themselves apart, piece by piece, in a Russian doll sequence. One crane would lower parts of another. The last crane, stripped to its bones, squeezed through the elevator shaft to the ground. With the crown in place, finishing touches began. It takes 3 months just to clean the windows. The spire acts as a giant lightning rod, channeling desert storms safely away. Inside, the raw concrete gave way to marble, gold, and silk. The Armani Hotel opened its doors. The world's highest swimming pool and the highest mosque welcomed their first guests. The impossible tower was now a living monument. But every day, a small army returns to scrub the glass and keep the lights on. Proof that even at 828 meters, the work never really ends. The Burj Khalifa stands as a warning and a wonder. Proof that even the limits of geology bend to human will. But every superstructure built on risk demands vigilance. As cities race ever higher, the ground beneath us reminds us ambition leaves a footprint, and not every foundation can bear its weight.